Hello there. In this series, we've pretty much been focusing primarily on Riemann integrals in the Cartesian plane. For example, let us assume we have some curve and we have some boundaries, say A and B, and we're interested in finding the area underneath of this curve, right? So we usually represent this area by the integral from A to B of f of x dx. And that's of course assuming that this is the x-axis, the f of x-axis, and this is the curve, say f. So in this video we're going to explore a very interesting question, at least to me. Let's assume we take some curve in polar space. Right? So we have some curve over here that's characterized by some function, right? So we have two angles, right? Theta is equal to alpha and theta is equal to beta. And let's assume that this curve here is, say, r is equal to f of theta. And let us assume we're interested in finding this area. So, my question that I'll answer in this video is this. Is this area precisely the integral from alpha to beta of f of theta d theta? That is integration in the polar domain simply a change of variables and change of limits? Or is there more that needs to be added to this in order for this to be true? Alright, so we're going to try and come at this problem from an unbiased direction and pretty much forget everything we learned about, say, Riemann integrals, for example, right? So let's assume we have some area that is bounded by two vectors that is characterized by the angles alpha and beta, right? And let's assume we know that this is some curve, and let's call this curve, say, r of theta, right? Because in polar coordinates, usually we have two coordinate forms, theta and r, the radius. All right, so how can we approximate this shaded area? So what we can do is we can partition the theta interval, alpha beta, into smaller pieces. Let's assume we cut it into two pieces, right? So if we cut it into two pieces, what type of shape would best approximate this area? Well, it's definitely not rectangles, circles. More so, we can use triangles to approximate this, right? So there would be the first triangle area, and then we have another triangle area, right? So the sum of the orange and pink area would be an approximation to this bounded polar region, right? So the sum of triangle areas clearly is an approximation for the true area, right? And this definitely seems familiar, sort of how we did areas under Cartesian defined curves, right? So one characteristic that you should be able to see from this picture is that the more triangles we have, the better the approximation. And this is similar to how we did like rectangles and trapezoids before. The more shapes we have, the better the approximation, right? And the more triangles we have, the finer the partition of the interval alpha beta, right? So we have alpha, we have beta, and we take this interval and chop it up into really small pieces. So for each of these theta values, so we can call each of these lengths, say, delta theta, and there's going to be some r value associated to each of those, right? So let's look at a particular triangle, right? Let's extend that out a little bit. So there's some curvature here, of course, right? All right, so this angle here is going to be my delta theta, right? So this length here I'm going to call Ri, and this length here, I'm going to call Ri plus 1. And this, of course, is my curve R of theta. Right? So some properties you should be able to verify on your own is that if R of theta is continuous, or more formally, if R is continuous in theta, then if delta theta is approximately equal to 0, then Ri plus 1 is approximately equal to Ri, right? That is the change in terms of R is pretty much the same, right? Assuming that R is continuous, of course, and we're assuming that this is arbitrarily close to 0, right? So if that is true, if these lengths are pretty much the same, then that means this arc length is almost approximately linear, right? So therefore, area of region is approximately equal to the area of a circle sector, right? If delta theta is approximately equal to 0. And what do I mean by a circle sector? So pretty much these 2 points fall on some line, right? So we can use the area of a sector of a circle to sort of approximate that, right? Now there is going to be some area here, right? But of course the smaller this delta theta is, the smaller that area will be, right? So that's good. So let's try and build the area of a circle sector formula in case we have forgotten it. So the area of a circle we know is going to be equal to pi times the square of the radius of that circle. Therefore, the area of a sector of a circle, and let's assume we have a particular theta region, and we want to know the area of this piece. So we're assuming that that theta is between 0 and 360 degrees. So that means this is going to be theta divided by 2 pi times the total area, which is going to be pi r squared. So we clearly see that pi cancels, and we're just going to be left with 1/2 theta r squared. So if we go back to our approximation for the our region, then the area of our region is going to be approximately equal to, or equal to 1/2 times delta theta times Ri, the quantity squared, right? And this is what we're going to be working with. So, of course, this is just one of the regions, right? Because we're going to be summing up smaller and smaller regions over the entire region of interest, right? So the area that we're interested in is going to be approximately equal to the sum of the areas of all of these little baby triangles, right? So the sum from k is equal to 1 to n of 1/2 delta theta, which is going to be constant for all of them, times the corresponding radius of those sectors squared, right? So we know the true area is going to be equal to the limit as n goes to infinity of the sum from k is equal to 1 to n of 1/2 rk, the quantity squared, delta theta, right? So this, if the limit exists, is what we will define as the polar integral of that function, right? So we will denote it by the integral from alpha to beta of 1/2 r squared theta d theta. So therefore, the area is going to be equal to 1/2 the integral from alpha to beta of r squared theta d theta. And this is the formula that we want. So it's not quite the same as the Cartesian representation, where we were just adding up rectangles, because now we're working with triangles, which are sort of coming from circle sectors. So if we want to find, so if we have some polar region, and we want to find this piece here, then this we'll be able to get it. So this is theta is equal to alpha theta is equal to beta, and this is r of theta, right? So that's good. All right, so let's work through an example on how to calculate the area of one of these types of regions that is defined in polar coordinates. So the function that we're going to deal with is going to be r is equal to 1 minus 2 cosine theta. So let's do a brief review on how to sketch this curve, just in case you forgot. All right, so when theta is equal to 0, right? So this is going to be equal to 1, and then 1 minus 2 is negative 1, right? So if we start our theta at 0, then we're going to be located at negative 1, right? And you can slowly traverse this over here, and then you'll hit this point 1. So when it's equal to 1, this occurs when theta is equal to pi over 2. So this is theta is equal to 0. So you can plug in more values and notice that this curve will sweep around and go over here to minus 3. And this occurs when theta is equal to pi. And then this curve is going to sweep around over here. So it's going to be negative 1. And this occurs when theta is equal to 3 pi over 2. And then it's going to sweep around and come here, right? So let's draw the angles of traversion. Right? So it comes all the way back when theta is equal to 2 pi, right? So this is our curve. So what I'm going to be interested in finding is I'm going to look for the area of this little circular oval looking region in the middle, right? So by symmetry, we should only be needing to find 1 and then multiply that area by 2, right? So I'm going to call this area A, right? And this is the green area A. Alright, so we need to figure out what is the theta value when it touches the origin. So when r is equal to 0. So r is equal to 0. Theta is equal to what, right? Because we're starting at theta is equal to 0 and then going over to the origin. So we need to find the value of theta when that is true, right? So r is equal to 1 minus 2 times the cosine of theta is our curve. So we want to set r is equal to 0, right? Solve this equation for theta. So we have 1 minus 2 cosine theta is equal to 0. So clearly cosine theta must be equal to 1/2. So I have that theta must be equal to pi over 3. So that's definitely the first thing that we need. So that means the area of our region is going to be equal to 2 times the area of that smaller piece, which is going to be equal to 1/2 times the integral from 0 to pi over 3 of the function of interest squared d theta, right? So clearly this 2 and that half cancel, so everything's great. So I'm just going to distribute this out. So I have the integral from 0 to pi over 3, and that's just going to be 4 cosine squared theta minus 4 cosine theta plus 1 d theta. Alright, so how do we deal with this term? So remember, cosine squared theta is the same as 1 plus cosine 2 theta over 2. So it's just a rearrangement of our double angle relationship. So we can rewrite this as the integral from 0 to pi over 3 of 2, 1 plus cosine of 2 theta minus 4 cosine theta plus 1 d theta. And then I can integrate over this, or I can distribute this out and then combine like terms. Doesn't really matter, whatever you're comfortable with. But I'll just distribute and combine like terms just to make this clean. So I'm going to have 2 cosine 2 theta minus 4 cosine theta plus 3 d theta. Alright, so this function is actually pretty easy to calculate. So we have the integral of 2 cosine 2 theta, so that's just going to be sine 2 theta. The antiderivative of cosine theta is just going to be sine theta. Antiderivative of 3 is 3 theta. And then by FTC, we need to evaluate this as theta goes to pi over 3, as theta goes to 0, and then subtract. So notice, theta is going to go to 0, so sine 2 theta, sine theta, and 3 theta are all going to go to 0. So we only need to focus on this pi over 3 term. So I have A is going to be equal to sine of 2 pi over 3 minus 4 sine of pi over 3 plus 3 pi over 3. So sine of 2 pi over 3, we should know from our unit circle that this is square root of 3 over 2. And then sine of pi over 3, also square root of 3 over 2 plus pi. And then this, of course, reduces to our answer of interest, namely root 3 over 2 minus 2 root 3 plus pi. So this is the area of our region of interest, which, in case you have forgotten our shape, so loops around. So this is the area of this little piece here, right? So that's just a brief introduction on how to find areas of polar curves, which pretty much boils down to this relationship, 1/2 integral of alpha beta r squared theta d theta, right? Which is definitely not quite the same as the integral from a to b of f of theta d theta in the rectangular coordinate system. So there's definitely a difference that definitely needs to be remembered here. Anyway, I hope you enjoyed this presentation. Hope you enjoyed.